Shen, who's going to give our final talk in this session.
Thanks, Rachel. Thanks, Mark.
Yeah. Awesome, great. And so our final talk is going to be given by Judy Shen, talking about differentially private set union.
Great, thank you so much. So I guess, hi everyone, my name is Judy. I'm a first year PhD student, and I'm really excited to be here today to share some work that I did during my residency with these awesome co-authors and mentors at Microsoft Research. So here's our talk on differentially private set union. And so as a motivating example, I want to let us to begin by thinking about text generation. So for example, with our smart inboxes, we might want to think about predicting a response for an email, or we might want to predict the next several tokens of a paragraph given previous context. And so if we want our models to work well, if we want something fine-tuned and relevant to the specific subject matter we care about, we might want private user data. And so we want to think about how to make this private. And so before going into our problem, I really want to motivate what we can do to train language models with privacy now. So there's two main methods. So in our first method, we can directly train a deep neural network that helps us predict the next word. And so we do know how to do deep learning with differential privacy. But something that maybe we don't know as much as how this training might affect accuracy. And more importantly, when we are using these, when we're clipping when we're clipping gradients by example, NLP practitioners like to use a bag of tricks when training huge models, such as shuffling examples in a certain way, parsing certain examples into many more sentences that make that makes the process a bit more complicated. And so even beyond that, this general problem of these huge neural networks is that they're hard to train. So for example, state of the art is trained with a trillion word corpus. And there's also some challenges to applying it in the real world. For example, it's difficult to interpret. You can squint at attention weights, you can probe and try to understand why certain predictions are made, but overall it's an active area where NLP researchers are trying to figure out how do we think about the question of interpretability. And perhaps most worryingly, it's hard to ensure safe or unbiased behavior. And so oftentimes these models might generate sentences that are offensive, and whenever they do, they instantly appear on Twitter as a shocking example of how language models are biased and unsafe. And so what is an alternative? So an alternative that's commonly used in industry is we can first learn a vocabulary of n-grams or sentences, and then we can find some ranking model to help us predict from this vocabulary. And so it's a bit more interpretable because we can just look at what our rankings are. It's predictable because all our output is in this vocabulary that we decide to use. And when we think about our differentially private guarantees, we can think about how the ranking model can be private, but actually the focus of our work is thinking about how can we ensure actually these n-grams and sentences we use for training are already private in the first place. And so something interesting to know is that when we're evaluating performance based on human judges or annotators, it's actually unclear which of the two work better. So for example, the GPT-3 paper discusses limitations that the model is repetitive, which human annotators generally rate lower on fluency when they see this repetition. So hopefully I've motivated a little bit on why we care about vocabulary extraction. And so this problem that we want to solve is that each user has some collection of items, maybe words, n-gram sentences, and we want to extract as many items as possible while ensuring user privacy. And once we have these items, we can then use it to train some downstream model. And so formally, the problem we propose in our paper is the differentially private set union problem. So if we let U be some unbounded universe of items, And our input is just each user has some subset of these items, and our output we want to be a set union of these items that are as large as possible while maintaining some epsilon delta dp. So intuitively, a single user should not affect the output by much. And so you might think, excellent, I can, sweet, I can apply my, my trusty histogram technique to this problem. And that's indeed where we're going to start. And so we can think about, first of all, starting to build a count-based histogram. So for example, when each user comes along, they have several items in their set and they just contribute a count to each of the items that they have. We add some noise, and then we release items that are above a threshold. And just to recap, privacy analysis here is just to make sure that that a single user doesn't change the final histogram by much, whatever definition of sensitivity we're using. But as you'll notice, the goal here in this technique, these techniques is actually to preserve the output noisy count to be somewhat similar to the actual true count. And this is a little bit different from our goal that we talked about in our previous slide, which is we want the biggest possible output set. And so what might be some drawbacks? So if we care about the biggest possible output set, we might have some wasted budget if users have fewer items than their budget. And so they can, in principle, contribute more weight. And so we slightly modify these count-based algorithms into a weighted version where user budget can be split equally among all the items in W. But I think more importantly, it's that items might have skew distribution. And this is particularly the case in natural language. So we know that for the natural language, word rank and word frequency follow this Zipf's law distribution. So certain common words are going to be way above the threshold, while others might be have a lot less. And so our intuition here is we don't want to waste user budget on the items that are going to be over the threshold anyways. And so this motivates the techniques in our work, which we think about smarter policies to allocate user budgets so we can get the biggest output set. So when we say policy, we mean a rule according to which users can use their budget to increase weights of items that they possess. And if an item is way above the threshold, then there's no point in wasting any budget on it. And so maybe your first thought is, okay, well, why don't we just, when a user comes along, find the item that's closest to the threshold and add all their mass, so then we can release that item. And so actually, if we take this greedy approach, we can think about how actually the difference between the final histograms can be arbitrarily large. So we cannot bound sensitivity in this case. And so maybe it's not private. And so perhaps it's non-trivial to design policies which keep sensitivity bounded. And so the technique we use in our paper is just to come up with these contractive policies, which give us bounded sensitivity, which then we could have privacy. And so we say that we can say that some mapping is LP contractive if the distance between two histograms after applying the mapping is smaller or equal to before the mapping. And so more generally, we can say that an update policy is contractive when this property holds in every step. So you can imagine, as we're using these clever policies, these different update policies, we can start with two adjacent histograms that differ by one user, and our final output will also be less than or equal to the original distance after applying a sequence of these contractive update policies. And so we can do this for L1 and L2, which gives us our different, which give us some options. So for L1, if we care about so we can think about intuitively, all we're doing is we're going from some vector of all zeros to some vector of all gammas, which is some release threshold. And so once an item already reaches this gamma or our desired release threshold, we can continue increasing the weights evenly. And if we want to bound L2 sensitivity, we have a policy Gaussian algorithm, which we're moving in the direction of all gammas for an LT distance of 1, which means adding to each item a mass proportional to the distance between the threshold and the item. And so we do some experiments. So using a Reddit data set of 200,000 posts from 170,000 users, we can compare the size of the output set of unigrams for each algorithm. So to recap, on this graph, the count algorithm is just adding user counts to each item. The weighted is we're just modifying a little to distribute user budget evenly across all the items that they have, regardless of it's over or the threshold or not. And the policy algorithms are the ones we described that cleverly allocate user budget according to some policy that is contractive. And so we see at various values of epsilon, our policy algorithms help us release a larger set as a final output. So main takeaways, language generation, we see applications all around us that can benefit from user privacy. And we might care about maximizing actually the size of the set of items we can use for training. And so in our work, we formalize this problem as the differentially private set union problem. And we give new algorithms tailored to this to show that they outperform previous ones. And we also have this general framework of contractive policies, which help us prove that our policies are actually private and may help inform other algorithms down the road. And so our code is here available on GitHub. And if you want to access the data or have some further questions or discussion on privacy in this setting of language generation, feel free to reach out. And yes, that's it for me. And I'm happy to take any questions.
Awesome. Thank you, Judy. TPDP crowd, same as usual. Raise hand or just unmute yourself or type things in the chat. And I see Salil is excited already for the question.
Judy, yeah, that's a really cool technique, this contractive mapping. It wasn't, so one question is, it's not explicit in your objective function when you ask for maximizing the set. It's not explicit that you want to like retain. Is it important to retain like the heaviest items? Like the most frequent words, I see how you don't want, why it's beneficial for them to not waste budget on them. It seems like your algorithm has a sort of a monoticity property that you're still likely to at least not lose those heaviest items, but is that anything that you try to formalize in your algorithm?
Yeah, very good question. So you're right, explicitly we don't try to preserve this different way depending on how often an item is, but what ends up happening is that, yes, a lot of users end up having the same items. So certain items are likely to be released no matter what. And I think maybe an interesting direction is thinking like, what if we have like different sets of users out of some pool? Like what set of items are always released versus not? And I think how often an item appears might contribute to that, yeah.
Thanks.
I see also Damien has a question.
Yeah, thank you for the talk and the work. It's really great stuff. I was wondering, so the policy algorithms, they require to read the entire input data linearly, one after the other, and to store the entire histogram in memory. And so for very large scale applications, the fact that you can't parallelize the read process might cause scalability issues. And I was wondering whether you have a solution to that, or you have ideas of how this can be made more parallelizable.
Yeah, great question as well. So actually, in production, this is a huge problem because user sets can be like very large. And so actually there's a fork to my repo that does this in parallel. And so that you can split some version of the histogram across different users as you update. And yeah, so that's a great question. Yeah.
Nice. Thank you. All right, so I think to stay approximately on time, we're going to wrap up the session now. Let me hit stop recording. Yes, I'm done.